Dear students, in this section, we will see here analytic function. Before going to study analytic function, you are advised to study about the continuity of the function and the differentiability of the function. Then we will go to the topic analytic function. So what is analytic function? A function fz is said to be analytic if we talk about the point at z is equal to z0. So function f is differentiable not only at z0 but at every point in some neighborhood of z0. It means a function which should be differentiable not only a single point in its neighborhood also. So if a function is analytic in the domain, then it is said to be analytic at each and every point in the domain. Some terminology that we use for the analytic function, that is holomorphic, regular, monogenic. So what we understand about the analytic function here, suppose we have given this point, a function is differentiable not only at this point in its neighborhood. It was differentiable at each and every point in its neighborhood. Not a single singularity we have in this neighborhood. Then the function is said to be analytic. If a function which is analytic in whole complex plane, then it is said to be entire function. For example, you can have the polynomial functions that are entire function. You know the polynomial functions are continuous and differentiable for each and every value. You can take fz is equal to z square plus 2 like that. So what we understand, suppose this is the domain of the functions which are continuous. This is the domain of the functions which are differentiable. It means few functions out of the continuous functions are differentiable. And the out of differentiable functions, the functions which are differentiable are analytic. And the functions which are analytic, few of them are entire function. So these are, we can, according to the set, we understand the set of continuous function is the bigger and its subset is differentiable, set of differentiable functions. Again, its subset is the set of analytic functions, and the same way we have the entire function. So we can go up to this level. Every entire function is differentiable. Every entire function is analytic. Every analytic function is differentiable, and every differentiable function is continuous. I hope so. It makes you clear about the property of function in the form of analytic and entire function. So some property we see for the analytic function, like Cauchy's Riemann equation, that are used to determine whether a complex function is analytic or not. So let us see what is CR equation. Suppose we have given a function fz in the form of u plus iv, where u and v are the function of x and y. So if fz is differentiable at any point z, then at this point the first order partial derivative of u and v exists and satisfy the CR Riemann equation. So let's see what is a CR equation. A function f has the component u and v, and u and v are both a function of x and y. So we can differentiate it partially. So del u upon del x, that equals to del b upon del y, and del u upon del y, that equals to minus of del b upon del x. So a function which is analytic, definitely it will satisfy the CR equation or condition. So if a function f is analytic in domain, then u and v satisfy CR equation. Now suppose f is given in the form of u plus iv. Then f dash we can write f dash is the partial derivative differentiation of f with respect to x. So that is del u upon del x plus I del v upon del x. Similarly, by using the CR equation, we can write del u upon del x that equals to del v upon del y, and this del u upon del y in the place of del v upon del x. So in this way we can define the different partial differentiation of analytic function. The CR condition for the analytic function, it is necessary. Definitely it is not sufficient. It means if a function satisfies CR condition, a CR equation, it doesn't mean it will be the analytic. But if the function is analytic, then definitely it will satisfy the CR equations. If these partial derivative, that del u upon del x, del v upon del x, del u upon del y, and del v upon del y are continuous, then the function is said to be analytic. So we can understand in this way, if the function is analytic, it means it satisfies its component u and v that satisfy CR condition, and the CR partial derivatives are continuous. If we can prove u and v satisfy CR condition and these derivatives are continuous, it means we are proving the analyticity of the function f. I hope so it makes clear about the analytic function. Some property we can see for the analytic function. It will have the same property like the real function. Suppose f and g are analytic function, then f plus minus g, f into g, f upon g all will be analytic. But for the fraction f upon g, gz should not equal to 0. If you find any singular point, then the function will not be analytic. Like gz, if gz is 0, we will have some singularity. At that point, function is not going to be analytic. Analytic function of an analytic function is also analytic. Like the polynomial function we have, it will consist of the number of analytic function. Entire function of an entire function is again an entire function. Again, we have the example of polynomial function. So if f is analytic, then it will be continuous, differentiable, and its derivative are continuous. Derivative of an analytic function is itself analytic. Now let us see some example related to the analytic function. The first question we have, if fz is equal to xy plus iy, then we have to show that it is everywhere continuous, but it is not analytic. For the continuity we will prove here. So f we can write in the form of u plus iv, where u is xy and v is y. Now we know that u and v are polynomial in x and y, therefore it will be continuous for each and every point. Another way we can say u and v have the partial derivative, so every differentiable function is continuous. Another way we can say, so in this way, if u and v are continuous, then its combination u plus iv will be also continuous. So first part is obvious. Now for the to take the function is analytic or not, we will go to the CR equation. So first we differentiate u with partially with respect to x and y. So del u upon del x we get y, and del u upon del y that we get x. Similarly, we differentiate v partially with respect to x and y. So what we get here, del b upon del x is 0 and del b upon del y is 1. Clearly what we see here, del u upon del x is not equals to del b upon del y. Also del u upon del y is not equals to minus of del b upon del x. So as you know, if the u and v does not satisfy the Cauchy-Riemann equation, naturally the f will not be analytic. So this simple example, we have learned about the continuity of the combination of the functions, and in which condition we can say the function is not analytic. So if it is said function, if it is asked the function is not analytic, we only prove this: it does not satisfy the CR equation, or the partial derivatives are not continuous. Come to the next question here. Suppose fz is equal to log z is given, then we have to find f dash z, and we have to show that fz is again not analytic. At which point it is not analytic? So by definition we have f dash z is what? Limit del z tends to 0, f of z plus del z minus fz upon del z. So limit del z tends to 0, the first function will be log z plus del z, then minus log z upon del z. By property of log m minus n, property of log, that is log m minus n, it is log m upon n, that we have written here. And now we simplify it. Limit del z tends to 0, log of 1 plus del z upon z upon del z upon z into z. So we multiply and divide by z to the denominator, and now we apply the limit here. It is 1 upon z, simple. As you know the formula, log x tends to 0, limit x tends to 0, log 1 plus x upon x, that is 1. So that formula we have used here. As you know, if delta z tends to 0, then del z upon z is also tends to 0. So these two things we have applied to get the limit, to apply the limit. Now fz is differentiable, but the condition is if z is not equal to 0. So at this point definitely a function is not going to be analytic. Except this point, except z is equal to 0, function will be analytic. So in these two examples, we have learned about the function, in which condition the function is going to be analytic or not, at property of some functions, definition of analytic function, what is analytic function, its property like CR equation satisfied, and partial derivative should be continuous. Later on we will come with the more good examples. So till you can subscribe my channel for a more update. If you like, then share in your social media. So thank you for watching this video. I hope so it make it clear about the analytic function. So if you like, so like this analytic this video, you can share it. Definitely you can subscribe my channel for more update, for more updated video on complex analysis. And if you have any question, query, definitely comment on the comment box. Thank you for watching this video. Thank you.